Today we're going to be looking at a video by Solve on covering Chernobyl, the impossible task. So the initial sarcophagus. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I'll claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
April 26, 1986. Chernobyl's reactor number 4 explodes, triggering the worst nuclear disaster in history.
These are excellent animations, and that look to be a pretty realistic size and modeling. Usually in a lot of these you see this ridiculous over-the-top explosion, maybe even with like a miniature mushroom cloud, but they're off to a good start here.
The reactor's core is exposed, emitting radiation equivalent to dozens of atomic...
Okay, alright, and now we're going with a stylistic choice here. None of the debris was green. Yes, highly radioactive, highly dangerous, but not green. If it was green during the real accident, that might have actually made it slightly less dangerous because people would be less likely to approach it. I don't know, maybe not.
Bombs every single day. Engineers faced an impossible challenge. How do you contain the open core when you can't even get close to it? I've spent hours digging through archives, reconstructing what might be the first animated model of this near impossible engineering feat, one that almost ended in complete disaster. My name is Torgeir and I'm a senior structural engineer.
Okay.
And this is the story of the Chernobyl sarcophagus.
Interesting, so someone's going to be looking at it from the lens of a structural engineer. All right.
The most complex building project in history.
That's cool, I just slapped it on there. Wow, this is some quality animation.
After the accident, a team of Soviet engineers, led by Lev Bocharov, was tasked with designing a structure to contain Reactor 4. Numerous design solutions were proposed, but only 3 were seriously considered. Each had to be judged on feasibility, cost, manpower, and most crucially, time.
Yes, so here, this was immediate disaster response emergency building. So rapid containment, minimize exposure as much as you can, and immediate relief, or as immediate as possible. So a lot of sacrifices were made. This sort of thing was not designed for long term, not like the new safe confinement structure that was built in 2016 on top of this. So triage engineering, if you will.
The mound concept proposed burying the reactor under a massive mountain of sand. But this would make Reactor 3 inaccessible. It could even cause the structure to collapse, potentially triggering another explosion.
You don't want to mess with the reactor that's right next to it. It's something a lot of people forget about it, is this was one of a 4-unit site. Planned for 6, though I think even at this point, those later 2 were probably off the table at this point.
The monolith concept involved encasing the entire reactor in concrete, turning it into a massive immovable brick. But there was a fatal flaw. Reactor 4 sat on loose, sandy soil. The weight of the concrete could send it sinking into the groundwater.
Secondary concern. Now, concrete would have been a great choice. It's highly shielding against radioactive materials, so it would more or less solve that problem, but you'd create a bigger one of the whole thing sinking. So, yeah, but... And these ideas sound kind of crazy, just dump a whole lot of whatever on it. But again, these guys were really pressed for time. So you don't want a real sophisticated, metastable solution that's only good under very specific conditions. You want it to work, and you want it to work fast.
Contaminating drinking water, or even worse, causing a large thermal explosion. That left the shelter of...
I mean, if you're building stuff in a configuration where it's going to cause more damage to the structure, that might be possible.
Project, later known as the sarcophagus.
The one that
Unlike the others, this design wouldn't disturb the unstable reactor. It required more planning, but it was the only option that didn't risk making the disaster even worse.
Yeah.
Увага! Громадяни Прип'яті! На Чорнобильській атомній електростанції стався інцидент. Об'єкт зазнав пошкоджень через пожежу, і рівень радіації підвищився навколо периметра 4-го реактора. Заради вашої безпеки ми розпочинаємо тимчасову евакуацію.
This is very well done.
Автобуси прибудуть до визначених пунктів збору протягом години. Будь ласка, зберігайте спокій і зберіть необхідні речі. Влада контролює ситуацію, і незабаром ви отримаєте подальші вказівки.
To build a shelter, workers needed heavy equipment, like cranes and concrete trucks, to access the site. But there was a massive problem.
Like the inclusion of armored vehicles in said convoy.
Entire area.
Now, armored vehicles would actually provide that much more additional shielding against radiation, be effective against alphas, betas, and gammas. Not so much against fast neutrons, but that's less of a concern at this point. Neutron dose is effectively zero because the neutron dose is only a factor when the reactors actually operate.
I was buried under deadly reactive debris. Lead-shielded and armored vehicles were sent in to push the wreckage closer to the reactor.
Yep.
In tight spaces, remote-controlled rovers were deployed, but there was another
Man, this is top-notch. This might be one of the better Chernobyl videos I've seen on YouTube.
obstacle. The reactor's roof. Unmanned vehicles were too slow.
Yeah, I'm okay with the green for artistic license at this point, and that's what most people think of when they think of radiation. But yeah, radiation fields were quite intense depending on exactly where they were and in the proximity of the debris. Dose rates can be in the tens to thousands of Rontgens per hour. That was the unit they throwed around a lot in the time period. Now, a Rontgen is approximately 1 rem. Rontgens you're actually using as to measure ionizations. It depends on what it is. For things like gammas and X-rays, it's actually a little less, about 0.877, but most people are conservative and just say it's 1 to 1. And that's a lot. Lethal doses can be achieved in a matter of minutes, depending on where you are. And it varied quite a bit because there are some... It's not like the reactor exploded in this nice little neat, easy to measure pile. It was a mess and uneven and inconsistent, and you could have massively different readings 10 meters apart from one to the other, from one spot to the other. After all, when you double the distance from the source, dose drops off by a factor of 4, and at 1,000 rem, that's an almost guaranteed lethal dose. At 400 to 600, it's about a 50-50 shot. At 400 to 600, that's an LD 50-60, so 50% of the exposed population gone in 60 days. So, yes, not only high, but irregular.
Extreme radiation fried their circuits in minutes.
Oh, yeah.
And yet, the roof had to be cleared.
That was one of the hottest areas in terms of radioactive dose, so yes, it can mess with radiation-induced electronics degradation.
There was only one solution: to send in people. This was the deadliest place on the planet, but despite the risk, thousands of men were sent onto the roof.
So despite the high dose rate, one, assume you can get an accurate reading. You can do it without incurring as many fatalities as one might think, and that's by sending thousands and thousands of people and giving them strict time limits. In some cases, they were a minute or two, which, assuming you didn't stumble or get stuck or something, if you stuck to it, you can emerge from it relatively unscathed. Still, a very dangerous job that would be a nightmare to plan from any radiological safety expert's perspective.
They were known as the liquidators.
Вони пообіцяли нам по 1000 рублів за очищення даху. Але ми знали про ризик. Наше спорядження було мінімальним. Бавовняний халат був занадто теплим для лікаря.
So on the note of the equipment, the best thing they could do for protection is not be up there for long, because a lot of this was high gamma dose, which, unless you're wearing a suit of lead armor, which you wouldn't be able to move in, you're still going to get a very high dose. So radiation protection is about time, distance, and shielding. Distance, unfortunately, you had to get close to the source. Shielding, it just wasn't enough. What they're wearing will protect them from alphas and betas. Of course, you could argue even wearing street clothes could protect you from alphas and betas. And they have the respirators that'll protect them from particulate matter, airborne contaminants, which is good, but against gammas, it's not going to do much. So the biggest thing they could do for radiological safety in this horrible scenario is minimize their time.
А свинцевий жилет надто важким. Нам сказали, що він захистить від радіації.
No. Actually, the lead vest is probably going to do more harm than good because it's going to slow you down. Because you're protected from alphas and betas without it. The respirator will protect you from inhaling alpha and beta sources, particulate matter, but it does have the potential to slow you down as well. Nah, the lead vests, you might as well go without.
Після кожної зміни наш одяг доводилося знищувати через забруднення.
Yep. Since a lot of this was loose, yeah, lots of contamination. The main thing that the coverall suits that they're wearing will do is prevent contamination, which means spreading the radioactive sources in areas where it isn't controlled. But they could have gone with something lighter.
Ми могли відчути, де були небезпечні зони. Радіація мала металевий присмак. Найсильніше він відчувався біля краю.
Cesium-137 was a particularly nasty source. It's metal, it can get airborne, it's a mess.
Даху. Що б ми не робили, нам сказали ніколи не заглядати за край.
Because there you get close to something that has very, very high dose. Hot particles and remnants of core.
As workers clear debris from the reactor's roof, a concrete foundation is being made around Reactor 4 to help contain the contaminated soil. To separate Reactor 3 and 4, a large concrete wall is cast between them. This was one of the most complex part of the project, requiring thousands of pipes to be cut, rerouted and reconnected, all while working in a highly radiation environment.
Those pipes aren't easy to cut. I mean, I know this is Chernobyl we're talking about and not exactly the safest reactor design, but just by virtue of having a lot of pipes, conduits, pressurized systems, those pipes are still going to be hard to cut and machine, even for a destroyed building. As in, it takes time, which is something that is in short supply.
At the same time, a perimeter wall is being built around the site, made of steel cages filled with concrete. This barrier provides an initial layer of shielding, making it safer for workers to approach the building with equipment.
Concrete, again, is a great shielding from radiation, one of many reasons why reactor containment buildings are made of reinforced concrete. Note that Chernobyl never had what would pass for a reactor containment building in today's reactor designs.
To get closer to the reactor itself, workers build a stair-like structure by casting concrete in layers. Contaminated vehicles and containers are even used as fill material. Staying at lower levels provides some shielding from radiation as they continue construction. Large prefabricated steel panels were used as formwork for the concrete walls, lifted into place with demag cranes. The largest
steel's good as shielding as well. Not as much as concrete, but mainly just due to those particular ones not being as thick. But steel, enough of it can attenuate gamma rays, but it's not as effective as something like lead. But lead, in order to get rid of most of it, you're going to need a good solid 8 inches of lead. There are stronger materials like tungsten, but more expensive and more difficult to machine into shielding.
Cranes in the world, and 3 are bought from Germany, but transporting them to Chernobyl is a major challenge. The roads and bridges leading to the site weren't designed for such heavy loads.
Yeah.
Some bridges have to be reinforced or even replaced.
Shielding is very heavy,
and materials must be transferred between clean and contaminated trucks before reaching the construction zone.
That's one thing. In any radiological controlled area, you have to manage what is clean and what's contaminated. At nuclear power plants, for instance, they have regular tool rooms where you check out your tools that you need for performing any maintenance or operations related tasks. But there's also a hot tool room that exists within a radiological controlled area. Now, at the plant I worked at, so not Chernobyl, it's not like the dose rates were particularly high for working with those tools, but those tools were in a controlled environment, and they had there are various levels of contamination that they have, and depending on the level, you would be required to wear additional PPE if you're going to be operating that tool. And that would often include respiratory protection, especially if you're doing something that involves welding, grinding, cutting, that sort of thing.
Most of the trucks used for the operation were of the CRAS model. To protect the drivers from radiation, their cabins were fitted with a specially designed lead capsule, providing an extra layer of shielding during transport. A total of 400,000 cubic meters of concrete were used in the project, enough to form a cube nearly as tall as the Statue of Liberty.
Man,
to
that thing would be
support
heavy.
this massive amount of material, 3 dedicated concrete factories were built specially for the construction effort.
You would
The
need
western
to.
side of the reactor hall was enclosed by the western counterforce wall, a structure
Especially
made
to
of
do it fast.
prefabricated modules, standing 40 meters tall. Originally, these modules were designed to be filled with concrete. However, this step was never completed. Once the walls around the reactor are complete, work begins on the roof, the most critical part of the project. The main section above the reactor's core consists of a massive pre-built structure, designed to be lifted into place in one piece. This structure was known
And again, you don't want to have people building the structure on top of bits of destroyed reactor and very high radiation sources.
as the plane. By assembling it in a safe location, engineers minimized the need for on-site welding and bolting, reducing worker exposure to radiation. Structural engineers typically approach designs in one of 2 ways. One way is calculating a building from the ground up, where every structural element is planned and accounted for.
Sure.
The second and more complex way involves extending an existing structure. In this case, engineers must analyze the original building structural system, often without having designed it themselves. This can be challenging, as original drawings and calculations may be incomplete, lost, or even contain undocumented modifications made during construction.
Yeah, and this has a pretty big undocumented modification in that the building is destroyed. So trying to calculate that based off the original plans and and I know there's various estimating factors that I think the maker of this video probably knows better than I do as a structural expert, but the point is it's just not going to be nearly as accurate as designing from the ground up. I can wholeheartedly agree with that.
At Chernobyl, this uncertainty was even greater. The explosion had likely weakened the remaining structure, but the full extent of the damage was unknown. Adding to the challenge, the roof itself was one of the heaviest structural elements ever built. A collapse could lead to further radioactive releases, or worse, another nuclear explosion.
The second one, no, and also this wasn't a nuclear explosion in the sense that people think of when they think of, say, a nuclear bomb going off. This was an explosion caused by rapid pressurization, by the reactor's power level spiking to ridiculous levels is going to generate a ridiculous amount of steam, which causes extreme overpressurization, resulting in an explosion, and then a hydrogen explosion. So this wasn't, in this sense, a nuclear bomb like, say, the atomic weapons that were dropped on Japan during World War II. Not to diminish it, but even a secondary explosion in the event of a roof collapse, well, there's no fuel source for it because much of the reactor was violently ejected. There's not enough bits and pieces left over to start a nuclear reaction that is capable of causing another explosion at this point. Now, I agree with his initial point in that a collapsed roof would certainly make it worse because you could damage what you're trying to do to contain it and make subsequent efforts to contain it even more difficult and even more dangerous for people trying to contain it. So, yeah, still bad.
Failure was simply not an option. Fortunately, a specialized device was made for closer inspection, the bathyscope. This 25-ton chamber made of lead equipped with a small observation window, was the only way to examine the remains of the reactor structural system close up. The volunteers who entered this claustrophobic metallic coffin were called the cosmonauts, a name fitting for those venturing into the unknown.
In a
But
way.
there are chilling rumors surrounding these missions. Some claim that in moments of crisis, the bathyscap's door had to be opened, exposing those inside to direct radiation from the exposed core.
Like the Geiger counter effects.
Also, a blimp with a 40 kilowatt lamp was used for work during nighttime. The workers nicknamed it the chandelier, and it was later buried, being highly contaminated. During the inspection, engineers found that 2 existing ventilation shafts had survived the explosion, but they were never designed to support the immense weight of the plane beams, in a rather unsuccessful attempt.
That makes sense, because they're designed for ventilation, and air is heavier than you might think, but no, not for putting essentially a new roof or concrete or whatever their plan is.
They were filled with concrete. Meanwhile, on the west side,
animation.
the plan was to rest the plane beams on what was left of the central hall's walls. The massive DMAG crane was the only machine on the planet capable of lifting the plane into place, but the crane operator only had a grainy TV screen for guidance.
Wow.
To make things worse, the crane's maximum lifting capacity was 159 tons, the exact weight of the plane, but that
Man, that's not good. No margin for error there. And also, if the wind that also means if the wind blows a certain way, that you have more of a force. That you have a force of anything bigger than 159. That doesn't mean at 160 it's going to break, because there's some margin built with any sort of design limitations of everything, but you don't want to test it.
was without counting for the diagonal cross beams. The plane was lifted and everything seemed stable, but then, as they lowered the boom, a loud crack echoed through the site. People turned to see the unthinkable. The rear wheels of the crane were 1 meter off the ground. The entire machine was tilting forwards, balancing on its toes. For a
That's
moment,
nerve-wracking.
nobody moved. If the crane tipped over, it could crash straight into the exposed reactor. In a last-second decision, a 40-ton lead-filled
Put a
container
counterbalance.
was placed onto the crane's counterweight, slowly settling the wheels back onto the ground. Disaster had been avoided. With great relief,
Man.
the installation of the plane was successful. To add another layer of protection, massive concrete pipes were placed on top, originally meant to be filled with concrete, but because of the extra weight, they remained empty. Next came a web of steel trusses, before the top of the plane was sealed off with heavy shield plates. 4 additional beams had to be installed.
Love this
2
animation.
ran alongside the main roof, as well as the octopus beam and the mammoth beam. The mammoth beam was the largest beam in the entire project, weighing 50 tons. These beams would
Lot for
support
one
the
beam.
final shield plates and the so-called hockey sticks. The project is then finished off by reinforcing and covering up the remains of the turbine hull roof. In November, almost 7 months after the explosion, the sarcophagus was completed. The project required almost 90,000 workers.
And the reason why you're going to require tens of thousands, 1, you want to do it fast, and 2, people just dose management. Certain individuals are just going to hit their maximum dose rate depending on their job. And in the case of getting the debris off the roof in a minute or 2.
And the workers celebrated their completion by signing the last element that was installed. The sarcophagus was never meant to be a permanent structure. With an expected lifespan of only 20 to 30 years, it is now crumbling. That's why the entire sarcophagus is now enclosed by an even larger structure.
And this came right at 30 years. This larger hangar-like structure was built in 2016.
The New Safe Confinement, or NSC. This massive shelter houses a large crane, designed to dismantle both the old sarcophagus and the remains of Reactor 4.
So this project, I mean, they could have made it more durable, but it was never designed to be permanent. They just needed an immediate fix. If it was permanent, you'd put a hermetic seal on it to make it leak tight. And like he showed, some of these portions were put on structurally unstable components. So it was still unstable, but just still safer than leaving it exposed, obviously. But that being said, they did achieve immediate confinement to the point where radiation doses dropped dramatically after construction, and the Chernobyl exclusion zone is only slightly above background radiation now. This was a great video. Certainly one of the better Chernobyl ones I've seen. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.